Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. All right. So, well, let's hope that works in a second. There we go. Okay. All right. So yesterday we started to talk about residuals and. Okay. Let's see what happens. Nothing's happening. No one's back. They're all back. Oh, okay. Very good. Okay, so yesterday we started talking about residuals and we all got so excited that 5 to the hour passed and we went 2 minutes over. Oh my goodness. So that wasn't on the recording. So I'm going to try, and I can't actually remember what happened in that last 2 minutes precisely, but I got a pretty good idea. So we're going to try and have that discussion again. It's good, right? Because when you do a course, having things repeated a couple of times can help because you get to think about things a second time. Having things disappear every 30 seconds not so helpful, but anyway. Here, it'll come back. Here we go. All right. Well, we better start talking. Oh, what the hell is going on? Okay, let's hope this all comes back, and I'll start talking about it while it's on the screen, if it will. Come on. Otherwise, we'll be making another phone call. Okay, let's talk about residuals. So yesterday, I talked about constructing residuals for the low S curve. So I've got two plots here, left and right. On the left, we've got the data X. This is the rat data, so this is blood loss, and that's hormone level. And we have the relationship that does that. Okay, now you've got to watch my fingers. So in terms of the shape, starts down low, and then as it moves across, goes up, but the fingers get wider apart, right? So that's what it does. Okay, we're going to create residuals for that. Yesterday I struggled with it because I typed the command wrong. So let's... Excuse me for 1 second. I'm going to shut the system down and just restart it. Oh, g'day. I'm in Barry Drive, ground floor, and the projector gun is going on and off every minute. But I'm starting my lecture, so I can't stay on the line. 10 o'clock. But there's no point having one if we're going to have a strobe lecture, right? So I really need someone to come over here and sort it out. U8517524. Yeah. Yep. Okay. It's week. By the way, it's week 5, and this happens every week. Okay. Yeah. Well, something happens every week, so it'd be good if someone could maybe fix it. Okay. Thank you. He just writes down every week. Okay. All right. Okay. Shall we try? Let's try. Okay. So I wanted to create residuals. So to get residuals, basically you're taking the distance between a point and the point on the line immediately below it. So the trick is to try and get that point on the line. Okay, flashed. We're going to use a prox to do that. So what you have to do is you have to fit the low S-curve. So I've done that. I've just put it in an object called TMP. You can call it whatever you want. And then I'm going to use the X values in TMP and the Y values in TMP. That's my sort of set of points that I want to interpolate between. And then, okay, what I forgot to do yesterday, so I went a prox. Now you've got to imagine. I guess this course requires a good imagination, doesn't it? So we'll see if we have one. So you go a prox, brackets, then you give it the grid of points, $10 $10 Y. Then the thing I missed out yesterday, and the reason the thing didn't work, was you have to give it the points at which you wish to interpolate. So I want to interpolate at the original x's. So I go comma x here. And then I want the y values that come out of that. Okay? So I'm going to repeat that. Approx brackets $10 x comma $10 y. So $10 x $10 y is your set of points. Then I want to interpolate at the x values in this case. So this is called x. If it were a different variable, like it was called blood loss, you'd put blood loss there, right? So x is just the name of the variable. Then close brackets, $y says, tell me the y variable at the interpolant. Okay? So that's what it's doing. All right, it's got to be...
This original temp x, same with the x.
So temp is the low S-curve, right? It's the fitted low S-curve. So when you fit a low S-curve, it produces a list, and that list has two elements, an X element and a Y element. So temp dot... No, you're asking is the X the name of the variable. It's always called $X, okay, because it thinks XY, right? So it's always called... But if you do names of temp, you'll see the names that are given to it, and you'll see it's X and Y. Okay, so once you've got those approxes, you take Y and you subtract off the approxes. Hello. Yes. It's still, it's still doing it. Mm-hmm. It'd be way better than it going on and off every 30 seconds. Yeah. Okay. They're going to restart the system. I'm getting music and play it into here so that the people who are listening at home can hear the nice music. Feel like you're in an elevator, right? Apparently they were ready to talk to me. But maybe I'm 10 in the queue, who knows? Oh. Okay. Thank you. Okay, they didn't pick up. Goodness me. Okay, all right. So you take Y, subtract off your interpolant here. Okay. Once you've got your residuals, you want to plot your Y, your X versus your residuals. But that's all silly, isn't it? Let's talk about something else. It's every week in this room, isn't it? Something goes wrong. It's always a little bit different. Anyway, I'm not confident that'll stay up. Okay, so the next thing we're going to talk about after we talked about residuals was actually fitting the model. Okay, so let's talk about that, because we can have a general talk about that without me needing to write anything. So you've got XY data, and you want to fit the curve that goes roughly through the middle of the data. Okay, so how might you do that? Well, what do I mean by goes through the middle of the data? I mean that, well, one way to think of that, just in plain words, is the line should go close to some or most of the data points. I say some or most because there are going to be some data points that don't look like anything else. And we're going to think of them as outliers. But generally speaking, and we've been able to do this pretty successfully with our fingers, right? If I give you a point cloud, none of you have too much trouble taking the line through roughly the middle, right? You can do it pretty easily. And outliers, you're pretty good actually. Your brain is actually pretty good at dealing with outliers. You mostly just blank them out. Okay? So, what we're going to do is we're going to pursue a method that tries to minimise, if you like, some overall measure of distance between the points and the fitted line. Okay? Now, you know the answer to this question already. The way that's normally done is to use a method called least squares. Now, least squares goes back a long time, right? While this is on the screen, I'll see if I can show you something. Where are we? This is, where's least squares? The origin of least squares. Let's go here. Why is what's on my screen not on? Oh, okay. No, it's all good. It'll come up. This goes all the way back to Legendre, a French person, in 1805. He wrote an article in 1805 describing least squares. This is it, right? So I'm going to put this link up on the interesting links page, but not with an expectation that any of you will. Who here speaks French? Anyone here speak French? Nobody. Sacre bleu. Okay, that's interesting. Well, if you did read French, you could actually read this article, which is in French. If you actually do try to read it, and I don't recommend that you not read it, how's that sound? You will see that interspersed throughout there's mathematics, which you hopefully will be able to read because that's not in French. And this is where he develops the method of least squares. Okay, interesting. Least squares, so this goes back to 1805, right? So that's a long time ago, several hundred years, okay? That's how long it's been around. Prior to that, people didn't know how to fit lines to data. Right? They probably did what we do, get the finger and, you know. They couldn't plot it the way we do though. They didn't have a computer. They had to draw it all by hand. Now, least squares is based on the idea that you want to minimise some overall measure of distance between the points and the line. So I'm going to try and see if the document camera works. Let's have a look. Oh yeah, that's all right. Okay. So you might have data, and our data looks something like this, right? It's got probably goes up a bit quicker, like that. That might be our data, okay? And we want to put a curve through this, all right? Okay. Oh man, this is fun today. All right, you can imagine what oh no you can't. Okay, we're going to put a curve through that data. And then we're going to look at the distance of points from the line. Now, let's think about this. What is the distance of a point from the line? What is the distance of the point from a line? Here are some options. Okay, I could do this. Right, I could use that distance. Well, let me move it so you can see it. Okay, I could use that distance, right? So this is the point I'm interested in, and I could just come across here to the line, and I could use that. Oh, geez. I could use the horizontal distance, okay? So that's one option. I could use the vertical distance, right? So in other words, instead of going across horizontally, I could go down vertically, and I could use that distance. All right. Other choices. I could use the perpendicular distance, right? So that's option one. Option two would be this one. No, that's you're not seeing that. Oh, geez. Vertical, that was vertical. Or I could use the perpendicular distance, okay? Most people would say those are the three obvious ones, but there are many, many less obvious ones, for example, right? What's the distance between here and Sydney? Who knows? 300 kilometres? 280? Yeah, that's cool. That's right, roughly. Okay, is that a straight line? No, right? Well, you start in Canberra, so you know you're going in circles to start with. And then eventually you get to Sydney, and that's definitely not a straight line, right? So that's not a straight line distance, but that's the distance to Sydney. So you could come up with the vertical distance, the horizontal distance, you could come up with perpendicular distance, or you could just carve some path that looks like a road that takes you from the point to the line, and that's a distance as well. There are infinitely many possible distances you could use. Okay? So let's put that on the table. So we need an agreed measure of distance. Okay? So we use vertical distance here, and the reason we use vertical distance is because y, the vertical ordinate, is what we care about. We measure variation in the vertical direction, okay? We don't care about variation in the horizontal direction. We care about the vertical direction. Perpendicular's alluring, but if you remember Pythagoras' theorem, it's some combination of horizontal and vertical, and you're going to get a different line if you use that, and that somehow seeks to minimise this as well as this. And if you have that final distance, you know, that weird, I'm going to go to Sydney distance, you know, you could do that. Well, you'll see it when it comes up. So, weird distance. We're going to use vertical because y is what matters. The vertical ordinate is what matters. Okay, so that's thing one. Thing two, if we all agree that vertical distance is the thing to do, then we need to think of a way to minimise that, okay? So what we do is we take every point and we drop that vertical line from the point down to the fitted line, okay? And we sum up those distances, all right? Now, we can't just use the raw number because if points are above the line, they get a positive value, and if points are below the line, they get a negative value, okay? If the line goes through the middle, if I add up all those values, what should I get? 0, right? So I can't just use the raw signed distance. And that kind of makes sense to us as well, right? If I say to you, how far is Sydney? 280 k's. If I ask you how far is Albury, who knows where Albury is? It's on the border between Victoria and New South Wales, and it's about 280 kilometres in the direction opposite to Sydney. But we don't think of it as being negative 280 kilometres to Albury, right? It's still a long way to go, and we always think of distances as positive. So in the modern world, what we do is we'd measure these distances using an absolute value. We'd use unsigned different distances. We use absolute values, okay? So the formula you would write down for this is you would fit a line so that the sum of the absolute value of y minus the point immediately below it on the line is minimised. Now that's a mathematical problem. That distance is a function of two things. It's a function of the intercept and the slope, and then the data fills in the rest of the values, okay? And when I do get a screen, I'll write some of this down. But look, for the moment, we can just talk about it generally. Okay. I want to minimise the absolute value of y minus beta 0 minus beta 1x, absolute value, summed over all of the data. So that's a problem. It's a well-posed problem in the sense that I can think, there's my distance measure using the road. That's the curly line. Okay, I'm going to try and write something down. We'll see how we go. I'll write it down. I know you can't see me writing it, but anyway. Hopefully it'll appear when the screen comes up. Okay. So I've written a formula on the sheet there. You'll see it when the screen pops back up. It's not important. So it's the sum of the absolute value of these distances. Now, if you've got a function, so it's a function of the two betas. Function of beta 0, the intercept, and beta 1, the slope. All right. I've got a function of beta 0 and beta 1. I want to minimise it. What do I do? Differentiate, right? So the calculus helps us. So you take this function and you try to differentiate. So there's the function. You take this function, you try to differentiate it, you run into an immediate problem, which is the absolute value function is differentiable everywhere except at its minimum, where it's not differentiable. Derivative's undefined. So this is not a calculus problem. Now, that's not a problem for us today. We have computers, right? If I want to minimise a function, and it can be a weird function, then using numerical optimisation techniques, I can minimise it. So as a computing problem, this is a solved problem here in 2018. In 1805, not so much, right? They couldn't minimise pointy functions, functions that didn't have derivatives, okay? So Legendre in France, he wanted to minimise a function that he could differentiate. Now, he didn't want to use raw distances because raw distances have signs. You've got pluses and they're points that are above the line, and you've got minuses and they're points that are below the line, all right? And they cancel out. So he says, how do I take signed things and turn them into positives in a way that makes the resulting function differentiable? Square it. And so what Legendre said was use, and I'm writing it down and you'll see it when the screen pops up for the 20 seconds it pops up. Okay. Oh, it's almost there. A square is going to appear here miraculously the next time this reappears. Okay. Oh, there it is. Okay, so this is a function of beta 0 and beta 1. It's a smooth function. It has a derivative. You can differentiate this with respect to each of beta 0 and beta 1, and you can work out, set that equal to 0, solve for beta 0 and beta 1, you get an answer. That's least squares. So least squares has a number of properties that are really kind of cool. These properties are, it's been around since 1805, so it stood the test of time. The function that you're working with is differentiable, and so the answer is available in closed form. In other words, there's a simple equation for the answer. Okay? You don't need more than a hand calculator, and they didn't have those in 1805 either. You could do this with an abacus, seriously, because you've got a squared function there. The derivative of a square is linear. So the resulting equations that you get if you differentiate that are linear equations. Linear equations you can solve with a piece of paper. Okay? Really easy. Really, really easy. So least squares has been around forever because it's convenient and the function is easy to work with. Okay? But there are things wrong with it. And the things that are wrong with it is that squares take small distances and leave them kind of small, but they take large distances and they blow them out. So if you have an outlying data point, right, and so you imagine a point cloud can go up like our rat data. Imagine there's a rat that's sort of way, way up in the north of the plot, okay? When you try to draw with your finger the relationship that goes through that data, almost everybody in the room is going to ignore that rat, right? You're going to say, it's an outlier, it's a bad rat, I don't like rats. I really don't like rats. Ignore that one and my finger's not going to move. Okay? Hello. This thing's going berserk, yeah. That's all right. We're talking around it. Well, we're seeing anyway. Okay, so it's really, least squares is really bad when it comes to outliers, right? It causes these massive distances, and I'll show you in a minute, hopefully we'll show you in a minute how that's going to work, okay? So ideally what you'd love to do is you'd love to use a function that didn't have that serious problem that outliers blew distances out. And of course the simplest thing to do would be to use that simple absolute value distance. Okay? And that's one possibility. Now, another advantage of least squares that I didn't mention is that when your data is normal, least squares turns out to give you minimum variance estimators. Okay? And that also can be proved. And the reason that happens is because the normal density is e to the minus something squared. Okay? So the log, well, again, you might not have done a course where this next sentence will make sense. If it doesn't, don't worry. The log likelihood of a normal is a sum of squares. Okay? So that made no sense to you. Doesn't matter. If it made sense to you, you'll go, oh yeah, so least squares should give me maximum likelihood estimation. Okay? So it's optimal in some sense when your data is normal. Okay? But here's the thing. When is your data ever normal? Right? And what about outliers, which are a real challenge to normality in some instances? Okay? So that's the question. So in R, there are multiple functions which will produce least squares estimators. They are LSFit. LS stands for least squares, so LSFit means least squares fit. So that's a function. It takes an X, it takes a Y, and it gives you the least squares fit to that data, linear fit. There's LM, which stands for linear model. That implements least squares as well. Then, if you load up a library called MASS, which is produced by two guys, it's part of Base R now, MASS, capital M, capital A, capital S, you get access to a function which fits more robust regressions, okay? Regressions that use different distance functions, okay? So there is a function called L1 fit, which is an alternative to LS fit, and it implements that function, which is just the absolute value. It implements this one here. Okay, that's L1 fit. So LS fit or LM does this, L1 fit does this. All right, we might be back on the air. So far, so good. Well, we're back on the air in the middle. So if you're sitting over this side,
that one should be.
oh, it'll come up. Okay, I'll talk slowly. Okay, so I'll just write on this, hopefully it'll work. So L1 fit does this, LS fit and LM do this. If you guys want to move over to the other side, it's all good. Want to give you 2 minutes to move? You happy where you are? Not happy? It's all good? Okay. Watch it later. Yeah. Netflix is better, got to say. But anyway. Okay. So, here's our conundrum, right? This distance function, convenient, test of time, differentiable, all good. This function here makes a lot of sense because it honours distance the way you think of distance, but not differentiable, harder to implement. No closed form answer. So if I gave you a pen and paper and I said, tell me what beta 0 and beta 1 are, you're not going to be able to write it out. You need a computer. This one here, you can just do a pen and paper. This one here is optimal if your data's normal. This one's not optimal when your data's normal. And we might think critically about that statement, right? Because it's kind of odd that L1, which is this distance measure that everyone thinks is how you should measure distance, turns out to not be optimal. Well, there's a very good reason it's not optimal. If optimal means minimising sums of squares, because the normal density has a sum of squares in it, right, then of course this is going to be optimal. It's not a fair fight, basically. This one has the right features for the normal distribution. This one doesn't. Okay. Nevertheless, what we could do is we could try to do something to marry these two together in order to get something that has some of the optimality features of least squares, but doesn't suffer the evil outlier behaviour that least squares suffers. Okay, so let's draw some more pictures to try to talk about that. Okay, let me. By the way, I'm ploughing ahead. I hope that's okay. I do apologise for the way this room is always crap. Okay, I do. I can't control it, but I can say sorry. Okay, all right. So, L1, least squares. And this is going to be what I'm going to call a hybrid method. So we're going to have three we're going to talk about. Okay. So the distance, d, is equal to the absolute value of z, and here we have in mind that z equals y minus whatever the line is. Okay. So for this one, d is the absolute value of z. For this one, d is equal to z squared. And for this one, we need to come up with a d. Okay, so these are our options for fitting. As I said to you, in R, this is L1 fit. In R, this is LS fit or LM. Okay, now we need to think about this one. All right, let's go back to this one here. Let's draw it. So that's what the function looks like. Absolute value of z looks like this. Okay? It's differentiable everywhere except in the middle, where you need it to be. Okay, so you can't differentiate it. These squares, the distance function, looks like that. Looks like a parabola. Okay? I don't know where this glare is coming from and I don't know how to fix it. Maybe if I turn, can I turn the light off? I don't know. I shouldn't mess with things, I'll probably break it. Oh yeah, maybe there's something on top. Yeah, anyway, this thing has about 1,000 buttons but 0 labels. So we talk, this course is about information design. This is bad. All right. Okay. Well, we'll push on. Today's the day for pushing on. Okay, what are we going to do on this side? All right, so it's right under the glare. Okay, so we like this one, but we like it out here, right? In here is where we don't like it because it's pointy in the middle. We don't like the pointiness. But out here, we're really fine with it. So we want something that's good out here. This one here, we don't like it out here because it's shooting up really quickly, right? So it's taking outliers and it's making their distances really huge. But we do like it in here, right? We like it in the middle because in the middle it's nice and smooth. It sort of shallows out. It's like a beautiful, smooth... It's what you want your plane to do when it's plunging into the ocean or to the ground. It's straight back up. All good, okay? But smoothly. You don't want to hit the ground and bounce. That's what the first one does, okay? So, we're going to do this. We're going to make it look like that in the middle, and then like that, away from the middle, okay? So this is a distance function, which is the unholy marriage of this one and this one, okay? It's like the normal one in the middle, but at the edges, it doesn't rise as steeply, okay? And yes, this is not differentiable at 2 spots, those inflection points, but that we don't care about that. We only care that it's differentiable in the middle, because in the middle is where the minimum is, right? So we essentially are moving our problem away from where it was causing us issues. So now we're okay in the middle. So this is a much easier thing to solve, okay? So these are all called weight functions. This is the L1 weight function, or the absolute value weight function. This is the L2 weight function, or the least square, or the squared error weight function. This one here is a hybrid. It's got a name. It's called Huber's weight function, and it's named after a guy named Peter Huber, who came up with this idea that, we'd love to do the thing on the right, but it's got a problem in the middle. The thing on the middle is what's been done since 1805. Can we do better than both? Answer, here's our answer. Okay, it's called Huber's weight function. Now, we do have to decide what these points here and here are. How are we going to decide where the tails begin? And this is where we get a hint from the normal distribution, right? If you think about the normal distribution, where's the middle and where do the tails start? Well, calculus can actually tell us the answer to that. If you look at the normal density, if you calculate the point of inflection, that is the point at which the second derivative of that curve changes from positive to negative, that is where the normal starts to tail off, right? So these 2 points here in Huber's calculations were the points of inflection of a normal distribution. They are at 1.345 and minus 1.345. Those are the values where we start those wings, okay? And the best thing is that if you're in R and you want to use this weight function, it's really easy. You have to load the mass library. So you go library MASS, library mass, and then the function you're looking for is called RLM, which stands for robust linear model. Okay? So we've got L1, we've got L2, and then this is kind of like L1.5. It's like L2 in the middle, like L1 at the edges. It's robust. It deals much better with outliers. It automatically downweights them, right? So if a point's way out on the edge, it doesn't get as much weight as it would under least squares. So it can't drag that line around as effectively as it otherwise would, okay? And so this, I think, would be our preferred option almost always. Okay? Now, when you're fitting models, you can use any one of these three, right? Remember, life is a series of choices. And, you know, when you go to the supermarket, you can't just buy milk. Right? Anyone gone to the supermarket, tried to buy milk recently? You can have milk with this protein removed, and milk with that protein removed, and milk that doesn't come from a cow, and milk that comes from a goat. You name it, right? There's choices, 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 okay? And when I go to the supermarket and I buy my milk, you can be right next to me and you can go, that milk's terrible, I hate that milk. But I like that milk, so I buy that one. Well, it's the same with this. Some people will use least squares no matter what I tell them, right? And you know the single most important reason why people still use least squares? It's in Excel, right? So 99% of calculations on this planet are done in Microsoft Excel. Isn't that sad? And if you want to fit a model using Microsoft Excel, least squares is there, built in. None of this other stuff is, right? This is why we're not using Excel. We hate Excel. No, sorry, we love Excel, but in a very hateful way. And so, you know, a lot of people do calculations because it's in the software and that's just that. And so least squares is dominant, and it remains dominant. I would be really surprised if in 300 years' time, people still aren't using least squares in Microsoft Excel version 422, right? Which will look just like Excel 1, but there'll be a lot more toolbars, right? So this one's dominant and will remain dominant, let's face it. But here's the thing, right? If you're going to do critical analysis of data, if you're going to use least squares, and you can, right? It's like when you go to the store and you buy whatever milk you want, you can still use least squares. But what I'm telling you now is that because of the way outliers are going to pull that line around, you need to be cognizant of that and you need to clean your data beforehand, right? In other words, don't buy the full cream milk if you've got a cholesterol problem. Buy the skinny milk, right? So if you're going to use these squares, you've got to have a healthy lifestyle in other ways. So clean your data of outliers, okay? What L1 does for you and RLM does for you is it allows you to be less worried about those outliers, okay? Allows you to be less worried about those outliers because they deal with the outliers somewhat automatically, okay? So here's my advice. This course isn't about fitting models, but you will fit some models as you go through, okay? And this by the way, let me be very clear. This doesn't apply to the first assignment, right? So I don't want anyone coming up to me and going, you just told us stuff that now I've got to change everything. Don't change anything. Just keep on going, doing what you do. But when you do the project and you have to fit linear models, right, some parts of the project, well, depending on which data set you choose, you might be fitting linear models. Think about what I'm about to say, okay? If you're going to use LM, that's fine, but we need to see evidence that you've gone through and looked for outliers first and done something about it, okay? Because there are outliers in data and you have to deal with that. If you use RLM, then you don't have to do that, okay? Or at least it's not as important to do that. So that's really where it's at. So everything I do from now on where I fit a model, we're going to fit a model in a second, assuming everything goes back to working, I'm going to use RLM, which means I'm going to load the mass library and then use this function. If you want to, no problem, use LM. It's not a problem. But again, you need that first cleansing step if you're going to do that. All right, so let's dive back here, where we have waiting for us this beautiful French document describing least squares, okay, which I'll put that up. I'll make that link live so you can, if you want to, you can try to read it. Okay, but assuming you don't want to do that, we'll go back to here. We'll finish the discussion I was having before, right? It's like that ad. You've seen that ad for broadband in Australia where everything freezes because you all come from countries where they have proper broadband, I hope. Yeah. So we'll try and finish this discussion. Apologies. Okay, so here's my low S fit. I was working through this, so I was trying to read it out without you seeing it. Now you can see it. So a prox says linearly interpolate. I want you to interpolate between the x and y points I get out of my low S fit. I want you to interpolate at the x values I have, and I want you to give me the y value back. That's all it's doing. So the residuals are what I get if I take y, the original data, and I subtract off the points on the line immediately above or below that y point. Okay? And then what I've done is I've plotted my x value versus my residuals. Okay? Now we talked yesterday, we did this yesterday for a linear fit where I used LM. And now you can see what's going on. So here, remember we took our two fingers and we said, okay, this thing's moving, it's flat, and then it starts to rise. But your two fingers have to get further and further apart. I'm going to have to use two hands, it's so big. So zzz, and then by the time you're out here, your fingers are this far apart, right? Try to do that with one hand, can't. Okay? But two things have to happen. Your hand has to move, and these move as well. Everything's moving, okay? This one here, your hand stays flat. Just moves along pretty flat, and like that. Now, again, I talked yesterday about the two advantages of residual plots. The first is that it flattens the original plot. So that's advantage one. Advantage two is it changes the scale to make small differences rather more visible. So here in this original data, my y data goes anywhere between about 0 and about 50. So that's a range of 0 to 50. Okay, you'll see this one here, the range is now compressed a little bit. It goes from minus 20 to 20, so it's compressed, not a whole lot, but a little bit. And the reason it's not a lot more is because you've got a few points way up here. But generally speaking, if you've got a sort of a flaring out pattern and it's mild, the residual plot will let you see it a lot more clearly, right? Because it changes the scale to make that evident. It's like looking at something through a microscope, right? If I'm looking at this one, it's like looking at something sort of big picture, see everything. If I want to sort of hone in on only the variation features, I have to flatten the plot, and then I can reduce my scale to hone in. And it really does that rather well. So that's how that residual plot works, and I can see that flaring out. Now, to complete this discussion, I'm going to just take x and log y, right? So, because I think this linearises the plot. So there's the plot of x and log y. Lines, low s, x and log y. Okay, so there's my logged data. And if I produce a residual plot of that using low s, I would go temp is low s of x and log y. Okay, and then my residuals would be be log y, because that's my original y ordinate, minus approx, it'll be temp dollars x, temp dollars y, comma x. So I'm interpolating the low s fit at x, and I want the y ordinate, the vertical ordinate, and then I can plot x versus res, and there's my residual plot for the logged data. And there's the low s curve that goes through that. Okay? So again, nice and easy. On this one here, fingers have to move up. Yes, it's easy. They move up in a straight line, but like that. Here, it's all flat, so you get that. So that's cool. Now, I have one more improvement to suggest, and that is this. Who likes using two fingers when you can use one finger? Right? Because with the two fingers, it's a bit hard because, see, we do this, right? You put your fingers here on either side and you drag them across. But it's really hard to get your fingers to do different things if that's what the data did. So, for example, my first finger, my index finger here, it can be sort of surfing along the top here. And my thumb, which is down below, it's surfing along too. But really, there's this sort of gap here. So what I should be doing is this. I should be keeping this one sort of flat, and this one's got to be moving at the same time. And you notice how when I try to do that, both fingers move because my brain's not smart enough, right? Two fingers is really kind of hard. Doing two things at once, you just can't do it, right? Sorry? P&O? Oh, no, I can't even play. No, I'm hopeless. I'm hopeless. I tried once, but it sounds awful. It's not good. I mean, Beethoven was deaf. That's incredible, right? Anyway. So what I'd like to do is something that only lets me use one finger. Okay. So what am I looking for here? I'm looking for basically my two fingers to surf along and be doing the same thing above as below. Why don't I just fold it? Right? Why don't I just fold it? And that's what people do. People do a plot not of x versus the residuals, but x versus the absolute value of the residuals. And that's what I get. And then a low S curve that goes through that. Now this low S curve has a different meaning to the other one. This is like the average spread as you move across. And you can see that's pretty flat. That's pretty flat. So this is called an absolute residual plot. And that's actually, absolute residual plots tend to be more useful than regular residual plots, again, because you don't have to worry in an absolute residual plot about what's going on above as opposed to what's going on below, that middle, okay? It's very hard, remember, apart from piano players, which I do accept, it's very hard to do two different things and keep an eye on both of them, right? Anyone who's got two kids knows that's the truth. So, absolute residual plots are generally a good idea. The other thing that you'd probably want to do, once you've got these residuals, is to produce a QQ plot of the residuals. So I make my plot square, QQ norm of res. This is my QQ plot of the residuals from my low S fit. So have a look at that. What do we think? The idea was, we're hoping that these are close enough to normal for us to be able to go ahead and fit models. So what are we looking for? We're looking for this to be what? I can hear people muttering. I assume that's the beginning of straight line, not the beginning of strangle that guy, he's hopeless. No? Okay. So answer. Yeah, so there's the QQ line. It's pretty straight for most of the way, but you can see starts to tail off here, starts to tail off here. This is a what sort of shape? S for Superman, so it's that nice S, right? So it's kind of S, right? So it's a little bit light-tailed. A little bit light-tailed compared to a normal, okay? Now, again, this is where you have to have one of those difficult discussions, right? The difficult discussion is this. When you sit in statistics classes, in first year and in second year, we say, this is the model, you know, linear model, y equals a plus b times x. Errors are normally distributed with mean zero, variance sigma squared. You go ahead and you fit it, right? And as long as all of those assumptions are satisfied, as long as the relationship is linear and the errors have constant variance and the errors are normal, these three things have to happen. If all three things happen, I'm done, right? My model is perfect. I am some kind of God, right? I understand my data. I can communicate what's going on in my data to you. Bow before me, right? That's how statisticians see ourselves in the world. It don't always work out that way. We've already worked quite hard with this data. We have an x and we have a y. So then, by some miracle, we worked out that if I take x and log y, I get a linear relationship. So the first penny has dropped, right? I need the relationship to be linear to fit my model. Assumption 1, satisfied. Assumption 2, constant variance. Wow, I did a low S curve of the absolute residuals and it was pretty flat. My variance looks constant. Yes, right? I want to fit this model. I've got linearity, I've got constant variance. I am on the way. I'll be getting royalty checks tomorrow if it all pans out. All I need now is for my errors to be normal. Close enough. Close enough. Bow before me, right? Close enough. They're near enough to normal. And that's kind of what you end up having to do, right? Because you've heard that old saying, right? Here's the old saying. You meet someone at a bar. No, maybe not at a bar. At a party. In a park, whatever. You meet somebody. You want them to be good looking, rich, good in bed. The golden rule of life. choose 2, because you ain't getting all 3. Right? They're either good looking and good in bed but poor, or they're rich and good looking and not good. Right? So this is what happens. Golden rule in life. You want 3 things? Choose 2. That's all you're going to get. This is kind of what happens in data analysis as well.